Hello, good morning, good evening, good afternoon, bore da, wherever you are watching this. This is the third in the series of my videos. I've got a series of videos now on shear force diagrams. We've done one with just a UDL, we've done one with just point loads, but this is the daddy of them all, because it's got a UDL and a point load, so it combines all of them. So this is a typical one you might get in an assignment from me, so it's worth paying attenzione. This is a shear force diagram, and we've got a beam with a point load of 5 kilonewtons there, 8 meters in, and a load across the entire length of the beam. The beam is simply supported by these two, no overhang. The overhang one is the daddy of them all, really. The UDL is 0.2 kilonewtons per meter, and we've got to find or draw the shear force diagram. Don't forget, draw really means with a bit of graph paper. I'm probably going to sketch this using a ruler and some pens. So, as in these questions, normally we've got to work out RA and RB. I'll keep saying it, make sure you get RA and RB correct before you move on, because if these two are incorrect, your graph will be incorrect, and you don't want that. So the first thing I'm going to do is work out these two forces, RA and RB, just like we did before. So sum of the forces equals 0, sum of the moments equals 0, clockwise moments positive, anti-clockwise moments negative. Force is moment times distance. Force is moment times distance. A moment is a force times a distance. So ignore what that just said. So a moment, always check what you write, because you never know. Moment is force times distance. Moment is force times distance, and the beam is in balance. So it's not going to go through the floor. It's not going this way. It's not going up or down. It's in balance. So we need to find reactions RA and RB. First thing we'll do, the first thing you should do, is convert this UDL into a point load. Make it nice and easy for us. So convert the UDL into a point load, and you should know by now. So we've got a UDL of 0.2 kilonewtons per meter, and it acts over 10 meters. It acts the entire length of the beam, 10 meters. So to convert that into a point load equivalent, we multiply the UDL value, which is 0.2 kilo per meter times by 10. So 0.2 times by 10. Shouldn't need a calculator really. 2000 plus the ENG, 2 times 10 to the 3, 2 kilonewtons. And don't forget, it acts halfway along. It acts halfway along where the UDL acts. In this case, the UDL acts across the entire length of the beam, which is 10 meters, which means this 2 kilonewtons acts 5 meters in, because 5 meters is halfway. So that makes it a bit easier for us now to work out RA and RB, or RA and RB, because we've got 2 kilonewtons there and 5 kilonewtons there. This 2 kilonewtons is the equivalent of the UDL, and that 5 kilonewtons was just there anyway. 5 meters in, this one's 2 meters from there, which means it's 8 from there. So I'm going to calculate RB first, because I can. You can do it the other way if you want to. So I'm going to calculate RB, and I'm going to make this point here my pivot point, and I'm going to work out this force here. Force times distance. So here's my first force, 2 kilonewtons times by 5, because it's force times distance. This 2 is trying to make this beam go that way, which is clockwise, so I'm going to make it positive. This 5 force is going to be 5 times by 8, because that's 10 and that's 2, which means in there is going to be 3. So from there to there is going to be 8. So 5 times 8, 5 times 8, 5 times 8, that's the force, kilonewtons, don't forget. 8 is going to be the distance, and it's going to be clockwise, because trying to make this go that way. So that'll be that force and that force. RB is a force, we'll put it in, we're trying to find it. It's trying to make this beam go that way, which is anti-clockwise, that's why we get a negative number. And all that's got to equal to 0, because it's sum of the moments. So here we go, look. So 2 times 5. So a moment is a force times distance. Force times distance. So there's my force, 2 kilonewtons. There's my distance. It's 5 meters to there. It's going clockwise. That's why we've got a plus there. Here's my other one, 5 times 8, because it's 8 meters from there to there. It's going clockwise, so we've got a plus. 5 times 8. That's them two done. This one is going to be RB, which is RB, and that is 10 meters away, because it's 10 meters length of the beam, times by 10. It's going anti-clockwise, which you knows, the reason why I've got a negative number by there. So that's the sum of the moments. Don't forget they've all got to add up to 0. That's why I've got a 0 there. Don't forget to put the killer in. Don't forget I've just put the 2 and the 5. There is K behind it. So all I've got to do now is add that and that sum of the moments, which you can do if you want to. Don't really need a calculator to do this, but 5 times 8 gives me 50. So all of that is 50 minus RB times by 10. I've then brought this negative term over here by adding RB times by 10 to both sides. So 50 equals RB times by 10. Therefore, leave the RB over there, divide both sides by 10. That gets rid of that, and we'll have the 10 over there. 50 divided by 10 is RB, which in my book is 5 kilonewtons. So we know that RB is 5. Well, at the moment, I'm not quite sure, because you never know. But I'm going to put 5 there for now. 5, don't forget the K. So 5 kilonewtons. Now, as we've done before, what you could do is you know that you've got 5 and 2. So we've got 7 coming down, which means we've got to have 7 coming up. We've got 7 coming down because there's 2 there and 5 there. So there's 7 coming down, which means there's got to be 7 coming up. Forces sum of equals 0. Look. So we know this is 5, which means this, I reckon this is going to be 2. I'll put in brackets, guess we don't really know. Because this RA, RB and RA have got to be 7, because there's 7 coming down, which means there's 7 going up. We know this is 5, so 7 take away 5 gives us 2. So I reckon this is going to be 2. That's one way you can do it. I wouldn't advise you do it that way all the time, because if I got this wrong, if that 5 was wrong, then if I did it that way, that would be wrong. So if for some reason I work this out to be 4, I'm now going to be wrong, because 7 take away 4. It's going to be 3, which you wouldn't know until you drew the diagram or something like that. So what you should always do is use moments to do both. So what I'm going to do now is I'm going to take moments about point B to find what RA is. I've got a good guess that it's going to be 2, but I just want to just back myself up because I could have made a mistake, and people do make mistakes. So I'm going to make, so calculate RA now, take moments about point B. So this point here now, so that point there is going to be my pivot point in there, pivot point there, and this 5 is going to be going anti-clockwise, so is that 2 going to be anti-clockwise, and this RA is going to be going clockwise. So these are going to be negative, have to be positive. So force times distance, 5 times 2, 5 times 2. The 2 is halfway, so it's going to be 2 times 5, because halfway, look. And then RA is 10 meters away. So calculate RA, so moments about point B. So 5 times 2, there's my 5, there's my 2. It's going anti-clockwise, that's why I got a negative number. 2 times 5, there's my 2, and it's 5 meters away from this point. It's going anti-clockwise as well, so that's why I've got a negative number there. Plus, because we're adding these moments up, last one, RA is a force, we don't know what it is yet, put it in. It's going clockwise, it's going to be a plus, and it's 10 meters away from this point. So it's going to be RA times by 10. RA times by 10, positive. All equals 0. So these are the sum of the moments, so add these up. So minus 5 times 2 plus minus 2 times by 5 minus 20 plus RA times by 10 equals 0. I don't like this negative term over here, so I'm going to add 20 to both sides. So we move it over to here. So now I get RA times by 10 equals 20. Divide both sides by 10, which leaves me with RA is going to be 20 divided by 10, which is 2. Don't forget the K, so reaction A is 2 kilonewtons. So my estimate was fairly good because we've got 2 on this side now. So we've got, have I got a colour? So we've got 2,000 this side and 5,000 this side. So we've got 7 coming down now and 7 coming up. Because what comes down's got to go up. So we've got 7 coming down because we've got 5 and 2 coming down, which means we've got to have 5 and 2 coming up. 7 coming down, 7 coming up. Beam is in balance. Everyone's a winner. Sum of the forces equals 0. So RA plus RB has got to equal what's coming down. We've got 7 coming down and we've got 7 coming up. So 99.99% positive that I'm correct with that. If these weren't correct, then when we do our shear force diagram, everything else is going to be out. So you need to make sure, do it and do it and do it 3 or 4 times just to make sure that your reactions are correct. That's water. So now we've got the reactions. Draw a shear force diagram using point load, UDL and reactions. Like I've said in a previous video, when we're doing this shear force, right, you need to use the UDL. You've got to use the UDL. Don't use it like that because it's slightly different way because you've got a point load rather than a UDL. We've got a UDL, we've just converted the UDL there into 2 kilonewtons to make it easy for us to work out the reactions. So when you're doing the shear force diagram, you need to really put the UDL back in and use it. 0.2 kilonewtons. So now we've got a beam, we've got 5 here, we've got 5 there, 5 kilonewtons coming down. We've got 2 kilonewtons coming up there and 5 kilonewtons coming up there. And we've got a UDL of all of this, 10 meters worth at 0.2 kilo. So like we've done before, we just look now, let's whip this out, we just look at certain points to see what we can see. So we'll start at x equals 0. So at x equals 0, really there's going to be 2 points. We'll start off at 0 because we always do. And then what can you see? Let's use green. What can you see at x equals 0? All I can see, shear force coming up, is 2 kilonewtons, this force here. Can't see any of the UDL because we're not in the UDL yet, because 0. So we'll have 2 points. It starts off at 0 and then the graph will go up to 2. So next step is 2. Now, at x equals 2, all we can see at x equals 2, which is about here somewhere, is 2 kilonewtons coming up and 2 meters worth of the UDL. The UDL is 0.2 kilonewtons. Alright, don't do the mistake that I did and put 200 in here, look, because it's 2, that's 2 kilonewtons, that's 2 kilonewtons, so you've got using 0.2. So at 2 meters in, I can see the 2 kilonewtons coming up, and I've got 2 meters of the 0.2 coming down. So there's my 2, and there's my 0.2, which is my UDL, look, and it's 2 meters worth of it. So I've got 2 coming up, take away 0.2 is my UDL value, killer. Right, I've just left the K out for now, I'll put it in at the end. 1.6. So at x equals 2, my shear force is 1.6 kilonewtons. Don't forget to put the K in there. Look. 2, 2. X equals 4. So it's just straightforward. We'll just carry on now with the numbers. So at x equals 4, which is going to be this, so it's going to be there somewhere. So all I can see is this 2 kilonewtons still, and now I've got 4 meters worth of the UDL. So I'm 4 meters in. So 4 meters in, I've got the 2 coming up, there's my 2, and I've got 4 meters worth of the 0.2, there's my 0.2 kilo, 4 meters. If you notice, it goes up like 2, 4, 6, 8, 2, 4, 6, 8, 10, that. So quite easy once you know what you're doing. So 2 coming up, and we've got 4 meters worth of my 0.2 coming down. So in your calculator, if you want to, or do it in your head, 0.2 times by 4. There we are, make sure correct, yeah, equals that, do that, 1.2. Don't forget to put the K in. So at x equals 4, I've got 1.2 kilonewtons. X equals 6, so x equals 6, same thing, also all is changing really is I've got more of the UDL, so there's my 6, say. So ignore this side, just look what we've got here. So we've got 6 meters worth of the UDL at 0.2 and 2 kilonewtons coming up. So there's my 6. So there's the 2 as normal. There's my UDL value, 0.2 kilo, 0.2 kilo, and there's my 6 because x now is 6. So put that in your calculator if you want to take away 0.2 times by 6. 0.8 kilonewtons, don't forget the K. So then we'll carry on, we'll go now to x equals 8, which is here. We're going to have 2 points now because we've got this 5 kilonewton thing kicking in. Don't forget, a UDL is a sloping line on a shear force diagram, and a point load, which these are, a straight line down or straight line up. So we'll have 2 points now for this x equals 8. So at x equals 8, I've got the 2 coming up here, which is, there's my 2. I've got 8 meters worth of my 0.2. 8 meters in, and my UDL value is 0.2. That gives me 0.4 kilonewtons. So 2 take away 0.2 times by 8 gives me 0.4. And then I've also got 2 points. I've also got this 5 kicking in. So I'm going to have a point like that, and then another point straight down. It's not really, but it is, well, for our sakes, it is straight down. So 0.4, and we've also got 5 kilonewtons coming down. So I'm going to do 0.4, take away 5. Minus number, 4.6. 4.6. So we'll have 2 points, 0.4 and 4.6. Everyone's a winner. And then the last one of all is the 10, x equals 10. So we've got all of this now. So we've got 2 coming up. We've got 10 meters worth of the UDL. We've got this 5 coming in. And we've also got this 5 coming up. So don't forget, we need to come back to 0. So hopefully when you get to the end of the beam like this, I'm hoping that it comes to -5, because then I can add this 5 on to make it up to 0. That's one way of checking. If your reactions are incorrect, that is the way you will find out. And then you'll have to redo it. Now, if it's slightly out, it could be rounding. So hopefully I'm going to get -5 as one of my points, and then this 5 will kick in to go up. So at x equals 10, I've got my 2 as normal. 2 is normal. I've got 10 meters worth, because I'm 10 meters in, of my 0.2 UDL, 0.2 kilo. Take away the 5, which is that one there. So here's my first point, -5. Thank you very much. So 2 take away 0.2 times by 10 gives me -5 as well. Don't forget that. Gives me -5. So I can get 2 points -5. And then this thing here kicks in, which is the +5. B is +5. That's how we know we're correct. So now I'm going to get the +5 coming back up, which will bring us back to 0. Starts off at 0, ends in 0. Starts off 0, ends in 0. That is how I know I'm correct with my reactions. If you're miles off there, then you know your reactions are incorrect. Last bit we've got to do is just plot these numbers using a ruler and a pencil or a pen. Make sure you're correct if you can use a pen. So I'll go x axis 2, 4, 6, 8, and then my y axis I need to go up to about 2. That's the highest there, 2, and then down to about 5. Draw shear force diagram. So I've gone up to 4 and down to -5. That gives me enough room, because maximum there is 2 and -5 is my minimum one, and then 10 meters. So don't forget, at x equals 0, we've got 2 points. We've got 0 and we've got 2. So really we've got 0 there, and up comes the 2, because that is the reaction A really. So that comes up. So once you know what you're doing, you can sort of sketch these quite good. At x equals 2, I've got 1.6. X equals 2, I've got 1.6. Plot that. Sloping line for the UDL, don't forget, so it's a sloping line. When we've got UDL, when we've got UDL, you'll have a sloping line. X equals 4, 1.2. So it should be now, look, it's a fairly straight line if you've done your proper scale. X equals 6, I've got 0.8, 0.8. X equals 6, coming down nicely. X equals 8. Now I've got 2 points. I've got 0.4, 0.4. Plot that. Don't go from 0.8 straight down to there like that, because there's the line, comes to 0.4. Then we've got this 5 killer coming in at 8. So we've got that point, and then we've got this point here, minus 4.6. Plot minus 4.6 comes straight down. Don't forget, 0 shear force, right? Maximum bending. When we do the bending moment diagram for this problem, we're looking to get the maximum bending point, as in the top of the curve, like that, at x equals 8. Because at the moment we've got a 0 shear force at x equals 8 from the left, or 2 meters from the right, because it goes over x there. Look, it's naught there, isn't it? So all the force is now being put into bending rather than shearing. X equals 8. Last one is 10. Right, back here to press pause because I had an interruption. So at 8 is where 0 shear force and maximum bending. So we're expecting, when we do the bending moment diagram for this, to have a top of the curve like that. And then 4.6 comes there. We've got minus 5, and then we've got that point there, and then we've got a plus 5 coming all the way back up. Brings us back to 0, so the beam is in balance. So, lovely jubbly, nice and easy. Shear force diagram for a beam with a point load and a UDL. So if you notice, it comes up 2. Comes up now. Comes up 2, look. So it comes up 2, and then it kicks in with the sloping down line for the UDL, and then at 8, that's where my 5 comes in. 5 comes in, the UDL is sloping down like that, and then up comes my reaction of 5. So don't forget, point loads are straight lines up or down, and UDL are sloping lines like that. So if you're quite confident, you could have plotted that point and that point and just drawn a straight line like that. Obviously, the more points you do, the better you are and the more accurate you are. One last thing, make sure you get your reactions correct, because if your reactions are out, your diagram is going to be out. So that's all of that for now. So the next topic will be bending moment diagrams, which is slightly different. But for now, cheers and over and out.